Hi everyone, so we're group 5 and for our project we did the moment of inertia of various rolling objects. So in our group we have Ronan Bandari who's in mechanical engineering, there's me, Anand Genev, who's doing physics, there's John Lee who's doing electrical engineering, and Aaron Liu who's doing astrophysics. So we'll start off with the introduction. So in this experiment we will be testing various properties of moment of inertia, which can be defined as a qualitative measure of objects' rotational inertia. So in particular, we wanted to know how an object's theoretical moment of inertia matches up with its experimental values, how the moment of inertia is affected by the angle of incline that the object is rotating down, and also how the mass distribution within an object affects its value. So we tested a solid sphere in the form of a tennis ball, a hollow sphere in the form of a golf ball, and an ellipsoid in the form of a football. And to test the mass distribution, we used a empty, half full, and full water bottle, which acted as a filter. And all of the trials were done on both a 12-degree and a 16.2-degree incline, and the values were compared between both to see how the angle affected. And we hypothesized that the experimental value would be roughly equal to the theoretical values of moment of inertia. For the tennis ball, that was 2/3 mr squared. For the golf ball, that was 2/5 mr squared. And for the football, that would be 1/5 a squared plus b squared, which and a and b are the radii of the major and minor axes of the ellipsoid. And in addition, we believe that the moment of inertia would actually decrease with the amount of water in the bottle due to the higher concentration of mass closer to the center of the bottle. And finally, we hypothesized that the angle of incline would not affect the moment of inertia.
Hello, my name is John Lee, and I'll be going over the methods of our experiment. This is our experimental setup. We set up an incline, and on the top of the incline, we place the ultrasonic sensor. Ultimately, we are trying to collect tracker data and ultrasound data. The origin is going to be the starting position of the object. And at the bottom right of this slide, we have the mass and radius of our various objects. The mass radius of empty bottle is 300 grams, 3.5 centimeters. The mass radius of half full bottle is 580 grams, 3.5 centimeters. The mass radius of full bottle is 900 grams, 3.5 centimeters. The mass radius of tennis ball is 58.5 grams, 6.5 centimeters. The mass radius of golf ball is 45 grams and 4.27 centimeters. The mass and radius and length of football is 400 grams and 5.7 by 25.0 centimeters. So the steps in taking the data, we first measure the mass and radius of each object. Then we measure the angle of incline. And then we roll down the object on the incline. We will collect ultrasonic sensor data, and we will record a video of the object going down the incline and then analyze it using tracker. This is the ultrasound data for 12 degrees. We have the data for empty bottle, the half full bottle, the full bottle, and the football. We couldn't get the ultrasound data for the tennis ball and the golf ball because of the spherical surface. We couldn't get accurate data measurements. This is an ultrasound data for 16.2 degrees. This is a tracker data for 12 degrees. And this is a tracker data for 16.2 degrees.
All right, hello everyone. My name is Ronan Bandare, and today I'm going to be talking about the data analysis for our moment of inertia final project. So the way we found the acceleration, which we needed to find the moment of inertia for each of our position versus time plots, was by fitting a best fit polynomial to the data, taking the leading coefficient of the squared term from that, which is equal to 1/2 times a, and then multiplying it by 2 to find the acceleration. So those values are listed below each position versus time plot. This first slide here has the 3 water levels for our bottle collected using an ultrasound sensor on a 16.2 degree incline. This next slide is the same thing, but this time on a 12-degree incline. On this slide, we again go back to the 16.2 degree incline, but this time this data was collected using tracker. As you can see, this tracker data fits the best fit polynomials much more nicely. Again, using tracker, this time on a 12-degree incline. And down here in this bottom row of plots on this slide, we show the relationship between the multiplicative factor of F and the water level from our tracker data sets on the 16.2 degree and 12-degree inclines. On the 16.2 degree incline, there's a pretty strong negative correlation between F, which is the multiplicative factor of I, and the water level in the bottle. And that correlation coefficient went down on the 12-degree incline, but it's still there. In addition to analyzing the motion of the water bottles using with different water levels, we also wanted to look at the moment of inertia for a tennis ball, a golf ball, and a football. We used the same method to find the acceleration and F. With our tennis ball data, we found that we got consistent values of F for both angles, which is what we expect for a rigid body. Same thing with the golf ball. We found consistent values of F at both angles. On the football, using the ultrasonic sensor, we didn't find consistent values of F. And even using tracker, our values of F are slightly off, but this may be due to sources of error in rolling the football down an incline. This table on this slide here gives a summary of the values of F that we found. In this first column, we have the object that we were analyzing and the method that we used to collect its position data. These are each of the 2 angles that we used. And then in this last column here, we have what the theoretical F should be if these were ideal objects. And on this last slide here, we show the formulas that we used to calculate F for both the football and all the other objects that we used.
Hi, my name's Aaron, and I'll be going over the discussion and conclusions of our experiment. Now, the main objective of our experiment was to find the moments of inertias of everyday objects. And our first experiment, dealing with a water bottle, we hoped to find out how the amount of water in the water bottle affected its moment of inertia. And through this, we hoped to find out how water tank trucks could turn a corner and aircraft carriers carrying liquids could move through the air safely. And through our sports ball experiment, we hope to discover more about the mechanics of playing these sports by observing how the balls could travel through the air. Now, for our experiment, the ultrasonic sensor wasn't able to give us reliable data because there were often big unexplainable jumps in the data. And for some of the objects, the ultrasonic sensor couldn't even pick them up because the objects were just too small. And for our first experiment, the water bottle experiment, we found that there was a slight downward trend for the F value as the amount of water in the bottle increased. And this matched with our hypothesis, and we explained this as the water in the water bottle increased, the water would be closer to the center of the bottle, and thus the bottle could rotate more easily. Now for the 3 sports balls, in each of the 3 cases, the sports balls seem to have higher moments of inertias than the theoretical. So we explain this by saying because of friction and air resistance, the calculated A value, the acceleration, was slower than it should have been. And because of that, the calculated F value was also higher than it should have been. And in addition, the geometries of the balls may not match perfectly with what we modeled them with, and thus the moments of inertia may also be off because of that. And lastly, we found that the angle of incline does not seem to affect the F value. And this is because moment of inertia is based off of the mass and geometry of an object and nothing else. In the future, to improve our project, we could use different amounts of water in the water bottle, so we could get a smooth curve for the graph of amount of water in the water bottle and its moment of inertia, because right now with only 3 data points, we can't really tell whether it should be a straight line or some other sort of curve. And in addition, in the future, we could also use larger objects so that the ultrasonic sensor could pick them up more easily. And this could include using like a gallon of water instead of just a small water bottle, or maybe a soccer ball or a basketball. We would like to thank Thomas Sutter for help guiding us through this project and the previous projects. And here are our references. Thank you.